Okay, so welcome to today's first lecture in Computational Finance. The outline of this class looks like this. First of all, we'll talk about the general outline and the basic information concerning the course. We'll start with a small introduction and some motivational examples, what we will be looking at during the course of the semester. We'll turn to portfolio theory and systems of linear equations later on, and talk about the capital asset pricing model, a little bit about optimization, then a lot about portfolio optimization as one field where we actually need methods from optimization and computer science and mathematics to solve for an supposedly optimal portfolio composition. We'll talk about asset models, which I guess is a very obscure word for you now, but especially if you are majoring in mathematics, economathematics, you will see that asset models are just a few examples of stochastic processes. So we'll see a little bit of stochastic calculus here and talk about asset models, stochastic processes and stochastic models that can be used to model the time evolution of asset prices. So that's why it's called asset models. We'll talk about quadrature or numerical integration, which isn't used so often directly in finance, but you see this every now and then if you need to do estimations, especially in statistics. Later on, we'll talk extensively about derivatives and option pricing. Option pricing is where we need these asset models because for the underlying, we assume a certain stochastic process, and then we'll need to solve for the system of differential equations. We'll not solve for these, but I'll just give you the result, which is sufficient for us. And we'll talk a lot about Monte Carlo simulation as one means of solving this problem of coming up with an option price for an exotic option. Then, at the end, we'll talk about interpolation and splines, which is actually quite interesting. It's a field and an area in numerical analysis that seems to have no direct application in finance, but it actually has when it comes to the estimation of yield curves and how it's done by central banks. Okay, so this is the general outline of the class. I will talk about the general idea behind this whole class later on in more detail, but let's first go through some general information. This is a large module. It gives you 10 ECTS credit points. It ends with a written exam of 90 minutes. The questions will be posed in English. You can opt to answer either in German or in English, but please be prepared to encounter English questions only. Okay. It's an elective course in the MSc in Business Administration, but as part of the many agreements we have with other faculties, you can also take this class if you're studying, for example, mathematics, physics, etc. We have 6 weekly hours approximately. We have this 2-hour lecture. We have a tutorial with some exam questions. We'll have to see about how we manage during the course of the semester to translate all the examples. And we have a 2-hour financial modeling tutorial in MATLAB or Octave. You do not need this one. You do not need to be skilled in Octave or MATLAB programming, but it helps you because there's usually one question in the exam where you are given a MATLAB program and you are asked to interpret this program. It's quite simple actually, but if you want to apply the stuff you learn in this class on a computer, it makes sense to do it in MATLAB and to do it professionally. Okay, and it's a part of the specialization in banks and insurance and investment management. And I'm pretty sure you've already seen this. By the way, the tutorials are online only. You can only find the slides and the videos online, and actually the lecture should be enough for you to pass the exam. The tutorials are just meant to show you some basic kinds of questions you might encounter in the exam. Okay. Now, if you go to my website, you can find in the section on teaching, you will find in a short bit the slides. The password for the slides is, as always, sector #7G with a capital S and a capital G. And you can go to the course website, download the slides, download the data. There are also some MATLAB programs. I will be updating the site starting today, and you can already access the whole set of slides in German that should still be on the old page from last year. Okay. You can write me an email at any time, and as you've probably noticed, I'm recording the lectures and I will upload them publicly on YouTube. Okay. If you were wondering where to find the videos, go to the slides and you can see that you can touch this huge YouTube button, and if you touch it, you will be taken to the YouTube channel, and you can subscribe to the YouTube channel. Then you will be notified as the videos are uploaded throughout the semester. Now, I always have to give this short disclaimer that I cannot guarantee that all lectures will be recorded and all lectures will be uploaded. The simple reason behind is that the files are huge. They are usually 2 to 3 gigabytes large. It takes a couple of hours to produce these videos, so it's a very sophisticated process, and it sometimes happens that the files are corrupt. And if the file's corrupt, I have no possibility to retrieve the original recording, and then I cannot produce a video. So usually this happens once every semester over all my classes, but luckily not in this one. Okay. What's the structure of the test? The test is made up of several small questions related to the entire class. Everything we will not discuss in class due to time constraint will not be relevant, but for example, if we make it to slide 600, everything up to slide 600 is relevant for the exam. I'm trying to include as many small questions as possible. Why? I still remember in my studies, there were some professors who gave exams that looked like this. The German system of health insurance, 4 hours. Everything. So that was the question, that was the exam. The German system of health insurance, 4 hours time. And one was supposed to write everything one knew about the German system of health insurance, and you had no clue what was asked for. And the second problem was that if you hadn't learned about the health insurance system, you were screwed. Yeah? So I'm trying to include as many small questions on all the subjects in the course as possible. The general formulae should be mastered passively. You shouldn't learn all the formulae by heart. I am putting much more emphasis and focus on the economic interpretation of these models and these formulae. Okay. Now, next problem. The class used to be relevant for the German exam of actuaries, the DAV examination. Problem is the DAV changed its whole curriculum starting 1st of January 2018. So they have changed their curriculum. This course used to be accredited. It's still accredited. The problem is you cannot use it because they have changed the curriculum. And they've changed a little bit in the lecture. I cannot guarantee that I will be able to include all the new stuff from the German actuarial exam in this semester, and I cannot really guarantee that even if I do this, the German Actuarial Society will accredit this in time before the exam. But if you, as the lecture is still based in part on this exam in financial mathematics and investment management, you can retrieve. You can also go to the website of the German Actuarial Society, retrieve former exams of them, and they sometimes look similar to the ones I've done here, because, as I've said, this class used to be accredited by the DRV, and therefore the topics we are dealing with here are somewhat related to this exam. Okay. Again, if you need additional material for preparing for the exam, you can take the online exercise, the online tutorial. You can also take the exams from past semesters and use those for preparation. And again, we also have an online tutorial that is just for fun, I would say. So you can see how MATLAB works and how you can program in MATLAB. Some references, some literature. Some literature references. The first one, there are actually two textbooks this whole course is based upon. The first one is a very interesting book. It's Numerical Methods in Finance and Economics, a MATLAB-based introduction by Paolo Brandimate. A very good book. Very interesting, has a much larger focus on option pricing and derivatives, but it's in an introduction, and it's quite interesting to see. Now, I hope we have one textbook in the library, otherwise I have one upstairs. The problem is the book is quite expensive. I think it costs about 200 euros, so I wouldn't recommend buying it. The second one is Albrecht Maurer, Investment und Risikomanagement in German. This is not very hard on the mathematics side, but it's where most of the finance applications come from. And actually, Albrecht and Maurer are the two colleagues who also work with the German Actuarial Society, and they usually give the classes for the German Actuarial Society. So their book is closely related to the German Actuarial exam, and that is why it's related and relevant here for this class. There are also other books. For example, Miranda and Fackler, Applied Computational Economics and Finance, and also this one's special, Paul Wilmot on Quantitative Finance. Paul Wilmot is, now he's a character. He used to be, I think he did his PhD at Oxford or Cambridge in physics. He then went on to become a trader and quant in the city in London. And then at some point, I think he put up his own investment fund, his own hedge fund, and he's now very active in teaching and consulting. And he created his own news magazine for quants, for quantitative finance traders. And because he's so active in this community, the journal or this news magazine is also called Wilmot. So if you ever see Wilmot, it's a magazine for quants, by quants. And he also wrote I think a 3-book introduction to quantitative finance. So he wrote 3 books. They are excellent. Again, they are very expensive. I hope we have a copy in our library. And this one is entirely not related to this course, and you don't need it at all. But if you are interested in the subject of quantitative finance and you feel that you still need and you still want to learn and read more about this, you should take this book. This is the absolute standard here. Okay. Now, I will also hand out a number of small data examples and data sets. Usually they are given in an easy to read easy to read format in Excel. Also some programs will be handed out, and I usually use R in my risk management classes, and here in this class I use MATLAB and Octave. I will talk about MATLAB and Octave in a bit, but you will see the algorithms could also be implemented in Mathematica or any other standard software you might want to use. Okay. Now, what do I want to achieve with this course? It's quite simple. As you might know, my background is both in business administration and mathematics. When I studied business administration, I realized that business is usually not too challenging intellectually. In many lectures, you simply learn a textbook by heart, and you formalize trivial results. For example, a company needs to make a profit. If you take revenues minus cost, you get profit, and so on. And I usually argue that if you have a natural idea of doing business, you can run a burger shop and earn $1 million. If you do it right, you can start your own business without ever having taken a business class. It's different with a lawyer and with a physician. You cannot work on a patient without having studied medicine. You cannot work as a lawyer or as a judge if you have no clue about the law. This is different in business and also to some part in economics. You can do business and you can become a successful entrepreneur even without having gone to business school. Then I studied mathematics. I saw that, mathematics is quite challenging intellectually, but usually mathematicians have no clue about the applications. They don't either have no clue about applications or they don't care about applications. And this is sometimes quite frustrating. So this course resulted from these experiences. I wanted to give a class on the intersection between finance, especially option pricing, and the part of mathematics that is called numerical analysis. In German it's Numerik, in English it's called numerical analysis. And usually numerical analysis is concerned with the computation of certain mathematical objects. Every time you cannot compute something analytically, you need to resort to numerical analysis to come up with a good approximate value, with an approximation. And this is what numerical analysis is all about. And this is reflected in the many parts of the lecture, in which we first talk about the financial and economic side of this theory. For example, we'll talk about portfolio theory by Markowitz and the capital asset pricing model, and then we'll talk a little bit how to optimize a function, and then we'll try to do portfolio optimization. Same with option pricing. We'll talk a little bit about Monte Carlo simulation, and then we'll apply it to option pricing. And last but not least, the term structure models cannot be done without polynomial and spline interpolation. So we'll need the mathematical background from numerical analysis to do this properly. Okay. Any questions concerning the organization of the course? Okay, so if you have no questions, I think I've already talked a little bit about this, that this whole class and computational finance as in general is more or less the intersection of finance and numerical analysis. One has to be careful. My interpretation of computational finance is a little bit different than to what you will find usually in the literature. In this course, you will see many applications in finance and its intersection with the numerical analysis. If you take a textbook or if you look at the literature, computational finance is usually synonymously used with option pricing. Why? Because unfortunately, option pricing is A, very important, and B, computationally demanding. So that leads us to the fact that usually if you hear someone talk about computational finance, it's just about option pricing, because this is the most challenging part in finance. Why do we need this? I would say back 30, 40 years ago, no one really thought about this and needed these complex methods from finance, from mathematics, to use in finance. But with the upcoming of even more and more complex and complicated financial products and financially engineered structured finance, traders and risk managers were more and more in need of methods to value these products. First question, does everyone know what financial engineering and structured products are? Structured financial products. Who does not know what financial engineering is and financially structured products? You all know this. Or you're just too shy to admit that you don't know what financial engineering is. I'm looking at the math students, and I don't think you have a clue what financial engineering is, so just admit it. Okay. Do you have an idea what financial engineering could be? Okay. Financial engineering is a very colorful name for doing the following. For example, if you buy a bond will usually have a cash flow stream that looks like this. Okay. Now assume you don't want this particular cash flow stream. You don't want to pay 100 and get 105, but you want a cash flow that looks like this. This is nothing that is even remotely related to a stock, a bond, or a bank loan, or any other traditional financial product. What you can do is you can go to an investment bank or any other financial institution that offers financially engineered products, and you can ask this investment bank, would you be willing to pay out 5, 8, I will give you 10 in the third period and then 15 again. The investment bank will say, of course, we can do this, and our price is 22.54. Then this is a financially engineered product. It's a structured product. Why? It's not related to a bond. It's not related to any basic financial product like a stock or a bond or a loan, but the cash flow stream is engineered. It's artificially constructed. And why would someone be willing to buy such a product, or why would someone want this? Funny anecdote. Perhaps you have seen the movie The Big Short. There is a scene in which Christian Bale goes to, I think, Morgan Stanley, and he asks for a CDS contract. He talks with the investment bankers and tells them, I want to buy insurance against the default of these and these and these mortgage-backed securities and these funds. And the investment bankers say, yes, we can sell you this, and we'll come up with a price. And he just says, okay, I'm buying it. And this is how you should think of financially engineered structured products. You, as an institutional investor, go to investment banks, you ask them, or you tell them what you want. You want to get a fancy cash flow stream or a certain type of insurance or risk management strategy, and the investment banks will usually sell you this product. It's not really a stock, it's not a security. Usually it's just an OTC contract, and in this contract you write, okay, A is willing to pay 5, 8, and 15, and B is willing to pay minus 10 and 22.54 in return. And then you draw up this contract, and this is the structured financial product. The interesting part is now here, someone has to come up with this price. If you go to an investment bank as an institutional investor and ask for this cash flow stream, someone has to calculate the price, the fair price, which you as an investment bank should ask for. And this is where you need computational finance. With this is quite simple. But usually these products are much more complex. They include derivatives. They have certain clauses. They are conditional on certain events being triggered. And this makes the valuation of these products quite difficult. And this is why you should then turn to mathematical models to value these structured financial products. Okay. And as markets have evolved and products have become much more complicated, so have the mathematical models. And you need sophisticated math models to calculate these prices. For now, this is the good thing for all the business and economics students. You don't need any detailed mathematical knowledge. We'll learn this on the fly, just as we walk through the course. The math students, let me just ask you, have you taken the class on numerical analysis yet? Yeah. Oh, okay, so most of these things will not be new to you. You will see similar things like in numerical analysis, and you don't need any large math background. Okay. And we'll start in a bit, but first let's talk a little bit about MATLAB. Why MATLAB? When it comes to mathematical standard softwares, there are pros and cons for every system and every program. For example, R is a very good for statistical analyses, especially in social sciences, but also in statistics. R is quite powerful. It has the disadvantage that the quality of the programs and the databases is sometimes not at the same level with all the packages. MATLAB is a commercial software created by the MathWorks company, and its name is derived from the matrix laboratory. If you want to buy MATLAB, you are free to do so. You can buy cheap student versions. They still cost $1, but you can also use Octave. Octave is the open source variant you can download for free from the internet. It's virtually the same as MATLAB. It's just not as fancy looking as MATLAB is. So there are a few slight differences, but for our purposes, Octave is just completely sufficient. Okay. Why MATLAB? As I've said before, R is quite powerful when it comes to statistics, but as soon as the computations are more computationally demanding, R is not the best choice, and you should try MATLAB. Why? MATLAB is not just a program that has some algorithms programmed in the background, in the black box, but it actually accesses pretty, I would say, famous and pretty powerful standard libraries, for example, like LAPACK. And it also employs functions in C and Fortran. Why? I've never learned Fortran. I learned C back at the university. From all I know is that Fortran is extremely fast. And if you need to do a lot of computations and a lot of calculations, you need speed, and then it's a good choice to fall back on something that is programmed in Fortran. Okay, and again, MATLAB is quite simple. It has no object orientation. It shouldn't really be called a programming language. It's quite simple, and you will immediately see how MATLAB works. Okay. This is what the MATLAB main screen looks like, and you can see it's extremely simple. This is where you enter your commands. For example, A equals 5, B equals 5, A plus B, answer is 10. Okay, so this is not what we would call a program language. It's just a command line where you can enter simple commands that are quite intuitive. Okay. I encourage you to try this out. This is quite simple, I think. Okay, so let's start with some motivating examples. And the math and math students I think they will like this. This is quite easy. First of all, who does not know what the Black-Scholes Merton model is and what it does? Okay. Do you know what a financial derivative is? What an option is? An option is quite simple. An option is the right, but not the obligation, to buy or sell an underlying security. For example, a stock option. The simplest option is a European call option. That is the right, but not the obligation, to buy one stock or 500 stocks or whatever of the underlying security, for example, Daimler stock, at maturity, when the option expires. This is the difference between a European and an American option. For an American option, you can exercise the option at any given point in time until maturity. Do you know what the third alternative is? What lies between Europe and USA? So this is an European option. You can only exercise it here. With the American option, you can exercise it at any time. And what do you call an option you can exercise at these points, but not in between? This is a trick question. What lies between Europe and the US? Asia. Okay, check your geography. No. If you had said the Atlantic, that would have been close. These are called Bermudan options because the Bermuda Islands are in between. So, yeah. You go the other way around. So these are Bermudan options. But we look at the simplest form, the European call option. Now, can someone of you tell me in 2 sentences what the Black-Scholes Merton model does? It's a price formula for the arbitrage-free price of a European call option. But how do you come up with this model? And I always stress this a lot because I think it's important to see how you can come up with this. Yeah?
I think the core is that the data is recorded continuously. So
yeah.
It's not a discrete model.
Yeah, that's true. Yeah, but how does the proof and how is the model working? I'll give you the general idea. You start with an underlying price ST. You simply assume that this is the diffusion process. More precisely, you argue and you assume that the stock price follows a geometric Brownian motion. Yeah? We'll see what a geometric Brownian motion is later on. It suffices to say that this is just a very simple assumption that the stock prices evolve in time in a certain manner. In the end, it will mean that the stock returns are normally distributed. So you assume a normal distribution, a Gaussian distribution for your stock returns. Under this assumption that the underlying price is a diffusion process, you look at the price of the option, and you realize that the price of the option is what? A function in time t and the underlying price st. We'll later on see, I think in the 6th or 7th lecture, we'll see that the option price, if you assume ST to be a diffusion process, does anyone know what happens if you want to look at the price of an option that is a function in time t and st again. Very simple result from stochastic calculus. This is the lemma of Ito's lemma. If this is true, then this is also a diffusion process, just with different parameters. So the stochastic process stays the same. It's the same kind of process, but the parameters change. And if you know this, you realize that this actually means that this is equivalent to what is called the, I hope I'm correct, the heat equation in mathematical physics. So suddenly you realize that this is, there's one step between. If this is this process, and if the price of an option is a diffusion process, the next idea is to ask yourself, when is the price of the option arbitrage free? You simply come up with the portfolio of stocks and the risk-free asset that pays out the same as the option. If it pays out the same, it has to be arbitrage free. It has to pay the same risk-free return. And no, I'm confused a little bit. Let me write this down. You do a portfolio of stocks plus options. Then you see that under certain assumptions, if you select the right amount, let's call it delta, a number delta of stocks, of options to the stock. This is correct. If you choose one stock and delta options, you somehow realize that this portfolio here should be risk-free. But if it's risk-free, in order to be arbitrage-free, it has to offer the risk-free return. And then you get a stochastic differential equation. It's an equation in which you have random variables and you have derivatives. And then you turn to mathematical physics, you solve for this equation, for this differential equation, and the result here is this price formula. This is the solution of the differential equation that comes up of this hedging strategy. When you put an option and a stock together in a portfolio, you choose the number of options to be equal to delta, and then it has to be risk-free. We'll see this later on, and you'll get the idea better, I guess, then. But this is how you can come up with this strange-looking solution. Because when I studied business administration, my professors only taught me, this is the price of an option, learn it, don't understand it, you will never understand it anyway. But the model is quite sophisticated and very elegant. The only assumption you do is that you assume that the stock price follows a geometric Brownian motion. Then you'll try to come up with an idea of when the price should be arbitrage free. You get an equation in which you don't have just numbers, but you also have derivatives of the same function. And you have to solve for this differential equation, and this is the solution under certain conditions. Before confusing you even more, does everyone know what a differential equation is? No. You probably know what a differential equation is. Who does not know what a differential equation is? Differentialgleichung in German. Okay. The simplest example is you take a function, let's write it in this way, f(x) equals first derivative of f. This is a simple differential equation. First of all, you need to know the solution of a differential equation is not a number or a variable, but it's a function again. You need to look for a function f that solves this differential equation. Do you have an idea what the solution is? Or what one solution could be? Yeah?
E to the power factor. E to the power factor.
The exponential function, yes. Yeah. This is one solution. Do you have another solution? Obviously. This is a solution. Yeah? Trivial one doesn't think of it. But you see the second important aspect of differential equations. Usually differential equations have infinite solutions. You have, first of all, you need to look for functions as solutions, and you usually have infinite solutions, and you need to single out one solution that satisfies certain conditions. For example, in this case, you could say, okay, we need this. This is a starting condition, and you see that this is no longer a solution if the differential equation has to fulfill also this condition. And by the way, what is the condition you pose and you require this, this in this Black-Scholes model? If we were to solve for this system of linear, for this differential equation, you would again get infinite solutions. But do you have an idea how you can single out one solution and how you actually come up with this formula? You do know one price of the option. When do you know the price of the option? For sure. At maturity. Because if you are at point capital T, if you are at the maturity of the option, you know that, for example, the call option will pay out what? You can sell the underlying for ST minus the strike if ST is larger than K and 0 otherwise. At the maturity of the option, you know what the option is worth. And then you use this as a final condition to solve for the differential equation. Mm-hmm. But now, let's all forget this and simply take as a fact that this is the solution of the Black-Scholes model, and this is a price formula for a European call option. However, we have come up with this model and this solution. So under the assumptions of the Black-Scholes model, the fair price, the arbitrage-free price of a European call option that does not pay dividends at time t is given by C0, this is the arbitrage-free price of the call option, equals S0, that is the starting price of the underlying, times the normal distribution at point D1, minus strike times exponential function to the minus RTth power times the normal distribution at point D2. And D1 and D2 especially have what as additional parameters? Maturity and the volatility sigma of the underlying. And you can see what influences an option price: the maturity, the risk-free rate, the current stock price, of course, but also the volatility of the stock price. And these are the main input parameters for the Black-Scholes Merton model. Okay. So this is the price, should be the price of an option. Then the question is, how can we calculate this? This seems quite easy. If I were to give you, for example, T is 1 year, S0 is 80, sigma is 3.4, and the risk-free rate is, let's say, 2.1%, you could simply plug in all those parameters in the formula. Seems quite easy. You see where the problem starts. One has to be careful when it comes to formulas like this. Where do problems start? This is the cumulative distribution function of the normal distribution. But that also means that, how does this distribution function look like? It looks like this. And this is one of the nasty examples of a very nasty integral that cannot be solved analytically. You can try as hard as you want, but you will not be able to solve this on a sheet of paper. So you need a computer to do this. Back 100, 150, even a couple of hundred years ago, mathematicians did this on paper. And do you know what they did afterwards? They wrote down all their results up to, say, 8 decimal points, and they put it in a book. And you still find books in which you find the tabulated results of these distribution functions, of other functions as well. And mathematicians looked up the results in huge, hundreds of pages long books in which these results were tabulated. Not a very efficient way, but again, at that time without computers, the only way to do this. Today, we are just slightly more sophisticated. We now have computers, and we don't need to tabulate this. The problem is that our computer still has to compute this, and it can only do, for example, your usual personal computer can only do it up to, say, 16, 20 decimal points. So you will, at some points, you will get rounding errors, because the computer will only give you a number that is exact up to, say, 16 decimal points. So we need to calculate the value of an integral. This is where later on we need quadrature and numerical integration. This happens quite a lot. Functions that at first seem quite easy because we know, well, it's the normal distribution, yeah, but at the end you still need to compute it. You just need to calculate the numbers of this function, and this can cause you problems. Okay. Then I will shortly show you some examples for cases in which you will see that some algorithms, some numerical problems differ with respect to their stability, their efficiency, their convergence speed, and also their condition, and we'll see what that means. But you can imagine that usually there are algorithms that are more exact, that are faster, that are more efficient, and so on, and you always know probably that the representation of numbers in a computer can cause problems, and you will get rounding errors. Okay. So let's look at this very, very motivating first example in MATLAB. We calculate 9 times 8.1 plus 8.1. And remember that decimal places and decimal points are shown with a decimal point and not a decimal comma in English. So it's the same in MATLAB, so you need to write 8.1 and not 8,1 as in German. So we write 9 times 8.1 plus 8.1, and the answer is 81, so everything is okay. Notice anything? Do you notice anything in the answer? Anything? What is striking when you look at the answer of 81? You get 4 zeros at the end. Let's just stay with this and look at the next computation. To round a number, we can use the function fix. It rounds the argument to the next natural number. And in this case, for example, if we fix 4.1, it gives 4. If we fix 4.9, it also goes down to 4. And let's fix this small computation, 9 times 8.1 plus 8.1, and the answer is 80 if we fix it. So what happens? Obviously, there seems to be something going wrong. And the answer is, if you first put in format long as a command, this tells MATLAB to not only give you 4 decimal places, but it should be 16. And you can see that the answer to 9 times 8.1 plus 8.1 is not just 81, it's actually 80.99999999986. And at this point, you should be quite disillusioned. You know, a computer, my computer, your computer, any computer is not able to compute 10 times 8.1. Something we can all compute in our minds. We don't take a second and the computer fails miserably with this. Why? The problem is that 8.1 seems to be a nice number, but for the computer it is not. And you can see this in a moment. But again, as the result, the actual result in the computer is not 81.000, but it's 80.99999. If we round it to the lowest natural number, then of course the answer is 80 and not 81. Okay. The explanation is quite simple. 8.1 has a finite representation in the decimal number system. So if you are calculating with 10 digits, this is a nice number. The computer calculates with 2, 1 and 0. And in the binary number system, 8.1 does not have a finite representation. I will show you this in a bit, but it's quite simple that there are numbers that have a finite representation in the decimal number system that do not have a finite, have actually an infinite representation in the binary system and the other way around. And these numbers cannot be displayed fully correctly in a computer. So what does happen? The computer sees this, it rounds the numbers, it cuts off the number at some point, and then you'll get a small rounding error. Okay. Another example, error propagation. You probably all know a system of linear equations and how to solve for a system of linear equations. Usually, a system of linear equation is written like this: a matrix H times a vector X equals a vector B. We are looking for this vector X, and this would, for example, look like this: times xn equals 1, and so on, or something else. So this would be a system of linear equations. How would you solve for the system of linear equations? You've probably done this at school, right? You use the Gauss algorithm. You would try to calculate the inverse of the matrix H, and then you would solve for this system of linear equations. MATLAB can do the same. It's quite simple. In MATLAB, you simply have to write H/B. Then MATLAB will do the same, and you could do this on a sheet of paper. So as long as the matrix is not too large, for example, a 3 times 3 matrix, you could solve for this on a sheet of paper. It would take you some time, but this is not something you would consider to be quite challenging, and a computer should do this quite quickly. Now we use this we use a special matrix in this. This is a Hilbert matrix. The Hilbert matrix has a special form. You can see that it's 1 over 2, 1 over 3, 1 over n, and so on, and it has this special appearance, and it looks in a very special way. Now let's do this in MATLAB, and you can imagine MATLAB again will fail miserably. We reverse engineer this, and we assume that the solution is 1, 2, 3, 4, 5, 6, up to 20. So we already have this solution. We then take the Hilbert matrix and we calculate the vector B. So again, we know H is the Hilbert matrix, we know X, and we calculate B, and then we just assume we've forgotten all about X, and we know H is this and B is this, and we solve for this in MATLAB. So B equals H times X. H is a 20-dimensional Hilbert matrix. Luckily, MATLAB has a standard function for this. You simply input Hilb and 20, the dimension, in parentheses, and then H/B. This gives you the solution of the system of linear equations with H as the coefficient matrix and B on the right-hand side. This is the solution and the output by MATLAB. 1. You already know now that this is not exactly 1. It is close to 1, and if we enter format long and we look at the decimal places after that, we'll probably see a little rounding error. So it's not exactly 1. 2.0011, it should read 2. Then 2.95, correct would be 3. 4.0, the correct answer would have been 4. And you can see that as you go down, you have errors that make this whole computation completely worthless. It's of no use. The funny thing about this is you can use any algorithm you want in a computer. With this type of matrix, this will always happen. And this is one fascinating aspect of conditioning and the condition number. If you take this algorithm and if you have this special setting with the Hilbert matrix, it's completely irrelevant if it's a 20-dimensional, 30-dimensional, these problems will always arise because of the special nature of this matrix. And this is due to the fact that it's badly conditioned. Intuitively, what do we describe with a condition of a mathematical problem? It's the dependence of the solution of the problem on the disturbance of on the input data. So if there are slight disturbances, slight errors in the input data, these will be magnified regardless of what algorithm you actually use. And in this case, MATLAB issued a warning. It told us that the matrix H is close to singular, but this is not necessarily the case. It could be that the problem is badly conditioned, but it could also be that the matrix is not close to singular. So the warning is nice, but you have no guarantee that MATLAB will always issue such a warning. Okay. So these are some motivating examples. You can see that even 10 times 8.1 will create problems in a computer. And you have to know about these problems and you have to care about these to get good results. Now let's start with number notation and rounding errors. First of all, you probably know we calculate in the decimal number system. And in decimal notation, for example, 1492 is 1 times 10 to the third plus 4 times 10 to the second squared plus 9 times 10 and so on. And you can use the decimal number system to express this number in this particular number system. Decimal places can also be depicted in this manner, so you can write 4 times 10 to the minus first, and so on. And you see that some numbers do not have a finite representation in the decimal number system. For example, 1/3, 1/3. This has not a finite representation, it's just 0.33333, and it goes on to infinity. So this is one example. Now, if we switch to the binary number system, for example, 21.5, you see that is 2 to the 4th plus 2 squared plus 2 to the 0th power plus 2 to the minus 1th power. And you see that this has the following representation, 10101.1. This is the binary representation of 21.5. And when you convert numbers from the decimal number system to the binary number system, you can see that this can sometimes cause a problem. And this is what happened with 8.1. If you take, for example, 7/10, so 0.7, it has a finite representation in the decimal number system, but it only has an infinite representation in the binary number system. And this is what happens with 8.1 or 8.2 or 8.5. It will always happen this way. Okay. And does the computer do? The computer sees this. It sees it only has a finite number of decimal places, and at some point it uses its machine epsilon. Each computer has a so-called machine epsilon. It's the maximum accuracy the computer can use, the maximal number of decimal places it uses in calculations, and at some point it cuts off this number and you get a rounding error. So suddenly 8.1 becomes 7 or 8.09999999986. And this is where rounding errors start. We don't need complicated calculations. It will immediately start with a certain numbers that are used in the computer. Okay, so we have rounding errors. We will also get so-called truncation errors when looking at certain mathematical functions. For example, take the exponential function. By definition, the exponential function is given by this infinite sum. So the sum of k from 0 to infinity of x to the kth over k factorial. This is the exponential function. But this also means that if you want to calculate the exponential function on your calculator, on your computer, you need to cut off this infinite sum at some point. By the way, why is it okay to cut off this sum at one point? Because the summons could also increase in size, right? No. Now, my dear math students, the sequence here needs to, in order for the sum, for the infinite sum to converge, this sequence needs to, ja, notwendige Bedingung für die Konvergenz von Reihen ist, dass die Folge der Reihenglieder gegen 0 konvergiert. Genau. This sequence needs to go to 0. Otherwise, this sum would go to infinity. It's quite clear. If something you add up, if the things you are adding up don't decrease to 0, don't converge to 0, at some point, the whole sum will just blow up to infinity. So a necessary condition for the sum to converge is the sequence of the parts here to converge to 0. So it makes sense that at some point, if this sequence goes to 0, that at some point you can cut off and say, okay, everything that comes after this is just 0. But of course, it depends at which point you truncate. If you do this after 10, after 20, after 50 parts and summons. So this, again, leads to a so-called truncation error. You cannot calculate this accurately, mathematically speaking, accurately in a computer. You need to truncate it. Okay. And sometimes you have something called cancellation, Auslöschung in German. Cancellation describes the loss of accuracy due to the subtraction of almost equally big floating point numbers. For example, take A and B. A is 2.345678, B is 2.346789. Both numbers are almost of the same size. If we calculate B minus A, we get 0.001111. And you can see, if you only calculate with 2 decimal places, you get a result of 0.00, so 0. And this is usually a problem. When you have 2 numbers that are almost the same, and you subtract A from B, or the other way around, you always get the problem of cancellation. That means a huge relative error when you compare the error you have by switching a decimal place compared to what you would expect. So the absolute error is quite small, but in fact, as you are expecting a very even smaller difference, the relative error of this estimation or this calculation is quite huge. And this is cancellation. Okay. Now for algorithms. we can distinguish certain properties. For example, stability, convergence, condition. And we'll see this in the following, but already you can imagine that algorithms and numerical methods will differ when it comes to speed, convergence rate, stability. Do they always produce the same results if you put in the same data again and again? And we'll start with stability. Now we consider a numerical problem, to correct this, which needs to be solved as a function f as a function of the input data x. So f of x is our numerical problem. We need to find this function. We have input data x, and we need to find this. The actual input data, they are usually disturbed. They have slight errors in it, so that we don't know x, but we can only observe x bar. X bar is x plus delta x, and this is the input data error. Yeah? Usually in finance, we don't have too many applications in which we have input data errors. There are some types, especially in high-frequency trading, there might be data errors. But this is, of course, highly relevant in engineering and construction. For example, if you were to construct this building, you get measurements of your material, properties, and so on, and you always have measurement errors. So the input data would be disturbed. The exact solution of the problem for disturbed input data is given by f of x bar. The algorithm, however, will only provide a solution y star. Now, why is that? You need to realize that there are actually two problems here at work. First of all, you have an error in your input data. And if your algorithm is working properly, it will use the disturbed data and would give you a result. What would happen if the data were disturbed? The second error comes from a faulty algorithm. So you will only get in the end y star. And y star, the solution y star, includes two errors. First of all, it is an input data error. And second, it's a change and an error that is coming from the algorithm itself. Is that clear? So you have two sources of errors. First of all, you have garbage in, probably garbage out. And the second problem is that the algorithm is probably including an additional error as well. And one needs to remember this. So what is numerical stability? An algorithm is called stable if the relative error f of x bar minus y star, you can just use it as an absolute number. If the absolute difference between f of x bar minus y star relative to the absolute number f of x bar has the same order of magnitude as the machine epsilon, and this is a machine epsilon. Yeah? So, what does it mean? The relative error you can see here is what? The algorithm is working properly, so you would get fx bar, and our observed results y star, compared to what we would expect. So this relative error only gives you the error that is included in the final result due to the errors in the algorithm. It's not the full error, because we are assuming that we start with the erroneous data in the first place. And this is why we call the algorithm stable. It doesn't change the original error in the input data. Yeah? So if this relative error is very small, we would call the algorithm stable because it does not worsen the error that is already in the input data. Again, we might have garbage in, garbage out, but the algorithm is not worsening the problem. then the algorithm is called stable. Then let's look at condition. What is the numerical condition of a problem? Let's look at this relation here. F of x, so this is what we are expecting. Correct algorithm, correct input data, minus correct algorithm, faulty input data, relative error when it comes to the expected true result, f of x, is smaller or equal than sigma, this is the so-called condition number of the problem, times the relative error between x and x bar. So what does it mean? Here, this is what? This is the relative error in your input data. And this is the relative error if your algorithm didn't cause any problems. If your algorithm worked just fine and didn't worsen the problem. So this condition number gives you what? It shows you that if you had an algorithm that includes no additional error, by how much your relative error in your input data is increased or decreased after putting the data into your algorithm. So for example, if you have a small relative error in your input data, your algorithm works fine, and you suddenly get a huge error in your output. As we've seen before for the system of linear equations with the Hilbert matrix, this condition or this problem is badly conditioned, and it has nothing to do with the algorithm. Any algorithm will produce the same result. You know? And this is actually the case here for the system of linear equations. You have a small error and we will see an even better example for this. You have a small error in your input data, and this small error in your input data is blown out of proportion by any algorithm, because the problem itself is badly conditioned. And this is what we call the condition number. It might also be that the relative error is decreased for some reason. It's quite nice, of course. Okay. This is a very good example, and I think this is one of the last few things we'll discuss today. Let's look at this standardized polynomial equation in the so-called monomial notation. Does everyone know, first of all, what is a polynomial? What is a polynomial? It's a polynomial function. It has x's in there, and it looks like a linear combination of x, x squared, x to the third, and so on. And this is no coincidence, because polynomials form a linear space, Vektorraum, linearen Raum. They form a linear space, and as any linear space, you can define so-called basis polynomials, eine Basis des Vektorraums. You probably know the three-dimensional real hyperplane. And it's quite simple. You have this vector space. And for example, this would be a basis of this linear space. And any vector can be represented as a linear combination of these three basis vectors. It's the same in the polynomial space. If you take the polynomials, you can see that you also get basis polynomials, 1x, x squared, x to the third, and so on. And any polynomial function can be represented as a linear combination of these basis polynomials. This is school knowledge. You've probably seen this in school. You probably did not know that actually polynomials also form a linear space, just like the vectors from high school. And it is also interesting to note that there is more than just one basis. There's more than one base, and you have more basis polynomials than you might think. This is the simplest form, at least for us, for calculating on a piece of paper. This is the monomial notation, Monomdarstellung in German, of a polynomial. But as you can imagine, there are several other basis representations. Do you know a couple of them? I can find one just very quickly. Let's see. Polynomräume. Oh, let's make it even Chebyshev polynomials. Let's take the English website. Chebyshev polynomials. They are an alternative sequence of basis polynomials. And if you want to know how they look like, for example, the Chebyshev polynomials of the second kind are 1, 2x, 2x times un minus un minus 1. And then you construct them recursively. So these are Chebyshev polynomials. You can use Legendre polynomials, Lagrange polynomials, and so on. And there are several famous and different basis polynomials. So this is the Chebyshev. This is a polynomial in the monomial representation. It's x to the 8th minus 36 times x to the 7th, and so on. And we want to find the roots, the zeros, the Nullstellen of this polynomial. And we can simply use the MATLAB standard function roots and put in the vector of coefficients of this polynomial. And we do this, and you can see that one has to be careful. Polynomials in MATLAB are not represented as 1 plus x squared and so on, but they always start with the highest monomial. So the vector has to look like this: 1 minus 36, 4, 5, 6, and so on. And only if you take the length of this vector, you know what a polynomial this is. So this is P1. And if we compute the roots, you can see that it gives us 1, 2, 3, 4, 5, 6, 7, 8 with slight rounding errors. But actually, this is no big surprise, because I simply constructed P by writing this and calculating it on a piece of paper. Yeah, so the roots are 1 through 8. Now, let's do the following. We slightly disturb the second coefficient by 0.001. And remember, we want to talk about the condition of this problem. So, we slightly disturb the input data, and the condition of the problem tells you by how much errors in your input data are worsened in your results. And you can see the results are now 1, 2, 2.99, 4.16, 4.57, 6.499 minus 0.7293 times I, the imaginary unit, and 8.27. The correct would have been 8. So this is also very fascinating. You have a polynomial, you have a minuscule error in your input data, and suddenly MATLAB again fails miserably to even get one root straight. Why? The problem is, and this is a well-known fact in numerical analysis, computing the zeros of a polynomial in the monomial representation is horribly badly conditioned. You should never do this. You do this in school, but if you were to solve for the roots of a polynomial, you would never use this representation. It's nice for us because we are used to equations like this from high school, but you should never use these polynomials, for example, to compute the roots. This problem will always happen, regardless of what polynomial you're using. And regardless of what algorithm you're using, the problem is that this problem is badly conditioned, and it's due to the monomial representation. The simplest way to solve this is what? Switch to another basis representation. If you were to use Chebyshev polynomials, it would get much better. So you simply do a shift and a transformation from the monomial representation to Chebyshev polynomials, and suddenly this problem goes away to some extent. Okay. By the way, does everyone know what this is? I did not know about this until studying mathematics, and some of you are already shaking their heads. This is what we call a complex number. Complex numbers, you can see this here. We start with the field of r squared, of the real numbers in 2 dimensions. So we look at real 2 tuples and define for 2 numbers, a, b, and c, d, an addition as well as a multiplication. AB plus CD is quite simple. You simply take AC and B plus D. But the multiplication looks a little bit different. The multiplication looks like AB times CD equals AC minus BD and AD plus CB. So outer minus, and okay. So this is the multiplication of the complex numbers. And you define this, and then you realize that actually this set of numbers, together with this multiplication and this addition, gives you a field of numbers in which you can find the same results, almost the same results as in the real numbers, but actually the complex numbers are much more interesting. First of all, R is a subset of C, of the complex numbers. It's quite simple. Any real number A, 0, this is a real number, and it's also included in the field of complex numbers. The nice results are here, for example, also every number except 0 is invertible relative to addition and multiplication, so you can always find the inverse. The same in the real numbers. For example, if you have 5, you can invert it when it comes to addition, or you can take 5 and you can invert it relative to multiplication. And the complex numbers are quite fascinating. First of all, you can also write the complex numbers not like AB, but you write A plus I times B, and I is the so-called imaginary unit, die imaginäre Einheit in the complex numbers, and it's 0, 1. Some results, first of all, if you square I, you get -1. And this is a result you will never find in real numbers, that if you have a number that is squared, the result will be negative, and in the real numbers. So this is strange. R is a subset of C, and for example, there are several results in function theory and complex analysis. You will find, for example, this is the main theorem of algebra. Every polynomial of the level n has n complex roots. Counterexample, x squared plus 1 equals 0 cannot be solved in the real numbers, but it can be solved in the complex numbers. So if you take this polynomial, you will only know that it can have up to 8 zeros in the real numbers. But you know, as a result of the fundamental theorem of algebra, that it has exactly 8 zeros in the complex numbers. And this happens here. And I only wanted to show you this because you can see that MATLAB does not only get the numbers wrong, it has to switch to a totally different set of numbers to even solve for this. And here, these are not complex numbers. They are real numbers, just MATLAB is doing not a great job of solving for the roots of this problem. Okay. So these are the complex numbers. Do you have any questions? If you don't have any questions, let's continue here next week. Thank you.